I'm going to focus on the fourth point of Mr. LaRouche's 4 laws, as has been said. And Mr. LaRouche put this out in a document a number of weeks ago, which defines the needed recovery program to save the United States economy right now. And he lays out a very clear structure of 4 legislative policies which are needed, culminating in starting with Glass-Steagall, followed by the creation of a national banking system, followed by the issuance of credit to rebuild the productivity and the productive powers of labor and high energy flux density employment of the U.S. population. And lastly, guided by a thermonuclear fusion science driver program for the economy. So we've covered these 3 points in a series, the first 3 points in a series of presentations. I'm going to focus on the 4th point. And since Mr. LaRouche issued this policy document, he's put increased focus and emphasis on a particular type of fusion and a particular orientation for this fusion driver, which is specifically fusion with helium-3 fuel, which is a particular type of helium, which is not your standard fusion fuel. And he put a lot of emphasis on the fact that there is a lot of discussion and orientation coming out of China to go to the moon and mine the moon for this excellent advanced fusion fuel, this helium-3 fusion fuel. So that has kind of upgraded and further put a clear focus on this fusion driver program needed for the global economy. Now I want to open by just referring to a few remarks that Mr. LaRouche has made on this helium-3 driver program. Over the past few days, he has been very focused on getting an increased emphasis on this orientation. And he said a couple days ago, he said, we need a helium-3 driver, and everything else on Earth from this lunar helium-3 driver is going to be subordinate to that program. Helium-3 fusion has to become the standard driver for the entire global economic system. He said the world is in a crisis, so in response to that crisis, to deal with this crisis, we have to go to the highest level of energy flux density to determine what it takes to get there, to get to that level, and then work back from that perspective. So the helium-3 program from the moon, as being driven by China's focus, is the solution to mankind's needs, both on Earth and in the solar system. This is what the future of mankind depends upon. And Mr. LaRouche said, obviously this will take some time. We're not going to get this in place tomorrow. But if you don't start, this will never happen. And making the commitment now will shape what you do tomorrow and in the short term and ensure that we actually can come out of this crisis. And he's had a lot more to say, but I wanted to kind of give a just quick focus on the emphasis he's put on this, that the entire recovery program has to be governed from the future backwards. That we have a breaking down of the global economic system. We have an orientation towards growth coming out of the BRICS nations, for example. Brazil, Russia, India, China, and South Africa, kind of leading an alliance towards creating a new global economic system in effect. And we have an entire world that needs to be developed, taken care of. And Mr. LaRouche has said, to do this, we have to not just go from the bottom-up approach, but we have to define what are the frontier challenges that are going to make the largest changes, the largest benefit for mankind's existence on Earth and in the solar system. Define those is what you need to focus on first, and then figure out what it takes to get there, what it takes to develop that. So I'm going to go through a number of pedagogical examples, illustrations, and try and put some more depth to this whole perspective. The creation of a fusion economy what that will do for mankind on this planet and in the solar system, and talk about what it'll take to get there. Now, I wanted to open, just because this is a very critical component, is just put a little bit of focus on what China is doing, and perhaps dispel some myths and lies about China's activity. There is a major top-down propaganda campaign to smear China, including coming from Obama himself, who, in an interview with The Economist, had some rather nasty remarks claiming China was nothing more than a cheap labor source and a more or less inferior part of the global economy, which is rather absurd and ridiculous. But the fact that he did that with London's Economist illustrates exactly who Obama is and who the British Empire is. But this is a ridiculous view. China is now leading the world in a whole array of technology development, and including emphatically space exploration, and a very clear and serious orientation towards the moon, towards developing the moon as a permanent base of operations for the development of the resources on the moon, the interaction of a lunar Earth economic system, and from that basis, the expansion out into the solar system from there, which is exactly what mankind needs right now. And the pivotal point in all that, Mr. LaRouche has emphasized, is again this unique helium-3 fuel from the moon. But just to kind of, I want to put out a couple anecdotal points just to kind of put some depth to this China orientation. There's a lot of material out there. It's not very hard to get a sense that that's a driving component in the entire global economy. But from a personal perspective, a couple of us in the basement have been having increased discussions with certain scientists, fusion scientists, working in the U.S. national laboratories who do very serious work on fusion. And the story of one individual, I think, encapsulates this reality rather well. On the one side, this individual has been either involved with or heading 2 separate fusion programs, which upon the day or a couple months after the completion of the initial construction and building of those fusion programs, they were then shut down. And all the funding was cut off before any serious experimentation could occur. So the entire program was built, the machines were built, they were constructed, and right when they were about to actually begin operation and investigation and useful science with it, they were shut down. Now this typifies what the United States has been doing for the past decade with regards to serious scientific work. There's been no serious effort to develop fusion power. I'm going to get a little bit more into that later in the discussion. And in fact, in reality, fusion has been suppressed in the United States. So now this individual, who had the unfortunate but illustrative experience of being involved in 2 very serious, very useful fusion programs, which were then shut down before they could even be utilized, he had also taken a few trips to China. And he recalled one of these trips where he had said that he was asked to come participate in a conference, scientific conference in China, which included fusion research. And in speaking with the people who were inviting him, they said, "What can you come and present?" And he said, "Well, I've done work in this area, I've done work in that area, and I've got this kind of half thought out idea for a potentially new type of fusion system that might or might not work, but I think it's interesting. I think there's some interesting potential there, but I've kind of just been thinking about that." And they said, "Okay, why don't you come and present on that idea?" And he said, "Well, I haven't built it. I got no support to build it. I really haven't thought all the details through. It's just kind of something I'm thinking about." They said, "That's fine. Come present on that." So he went to China, made his presentation, had discussions, whatever, what have you, then went back to the United States. I believe something like a year or 2 later, he went back to China for another conference. And lo and behold, he gets there, and they've built in China this thing that he had talked about the prior time he was there. They took his designs, his proposal, his concept that he was thinking about, and they just went ahead and built it. And they went to him and said, okay, what next? What do you want us to do next? So it's clear that, and this individual had also reported very forcefully that this idea that China is simply copying US technology or other European technology is a lie at this point. He said that certainly was happening over the past couple decades. You know, China was making an effort to catch up to the world in technology and science. But he said they've done that. They've absorbed much of it. And they have an entire generation of young, very bright, very forward-thinking scientists in a whole array of fields, including fusion, who are making original work. So he gave a very clear, from his personal experience, I think it's just a useful reflection of the overall global situation, where the US has stalled and stagnated on these areas, and largely due to the influence of this zero growth British Empire paradigm. Whereas recently, many nations, a number of nations, but very significantly China, have seen the collapse of this system and made a break for a new direction: pro-growth, pro-development, pro-nuclear power, pro-space. And so what we're seeing from China is very serious. Their lunar program is very serious. Just at the end of last year, people recall, they made the first soft landing of a lunar lander and a lunar rover on the moon since the 1970s. And they have designs for follow-up missions, and they have a lot of discussion and investigation going on at the Chinese Academy of Sciences, among other places, about how to develop the moon as a permanent base of operations, again, including the prospect of mining helium-3 fusion fuel from the moon to power the Earth. So this is what Mr. LaRouche said, this is something that we're not doing in the United States, but something which can save the planet. And therefore, Mr. LaRouche said, we fully support and fully back up what China is doing in this regard. And we will throw as much of our weight around as possible to ensure that we can make this the common goals and the common aims of many nations working together towards this objective. So now I want to also kind of dispel some additional myths about fusion science in the United States and the prospects of fusion science generally, just to kind of make sure certain basics are clear so we can get into the reality of the discussion. Now, there is a very bad joke floating around among scientists, among the population generally, that fusion is, in 1970, fusion was 50 years away. And then in 1980, it was also 50 years away. Today, it's also 50 years away. The running joke is that fusion is always 50 years away. And that's held up as something that hasn't necessarily been false under the current policies, but it's been held up as a claim that it's just too difficult, there's a lot of too many challenges, it's too expensive, it just can't be done, and it's always going to be, you know, maybe we'll get it in a century or a half a century, but it's, you know, it's not going to happen anytime soon. So that's the claim. That's what a lot of people believe. That is the result of the intention of policies, not the result of the reality of the science or the technology. I want to be absolutely clear on that. The major, most advanced fusion reactor being built right now internationally, this ITER project, which has some benefits, it has some limitations, it's not the full story, but it's certainly an important part of the overall perspective. It's not the end-all and be-all in and of itself, but it's a useful contribution to the whole effort. This ITER reactor, which is not going to be online until the 2020s, this thing was designed in the 80s, and this thing could have been built by the early 90s. the most advanced reactor that we're building right now is technology that could have been built by the early 1990s. We have not been held back by some insurmountable technological challenge. The policy has not been to develop what would be the most powerful energy and power source for the entire planet. And the idea that this would be too expensive and that the payoff wouldn't be worth it is just beyond absurd. This would revolutionize mankind's existence on this planet and beyond. I want to pull up a graphic here to highlight another expression of this same issue. This is based upon a study in 1976 on what it would take to build a fusion power reactor. 1976. Now this was the first very detailed, very thorough roadmap, so to speak, to develop fusion power. And they laid out a number of steps that would need to be taken. And they laid out in detail what it would take to take those steps, how much it would cost, how long it would take. And they came up with a range of proposals to bring an initial first generation of fusion power online. And a lot of it obviously depends upon support, funding this project to make it a reality. You can't do this if you don't get the support to do it. So they laid out a very clear program that said, we know what it will take. If we put the maximum effort into it, if we get all the funding we need, if we just give it to them and push the whole thing in a real crash program effort, in 1976, the assessment was we could have fusion power by 1990. That is the blue line here on the graph. And you can see that the corresponding amount of funding required to achieve that 1990 goal. They said if you take a little bit of a slower approach, don't quite fund it as heavily year to year, it'll take a little bit longer, but we could still have fusion power by, say, 2005. So that was kind of two. They have a few other ranges in there, again, depending on how much funding you give exactly. They also identified that if you just maintain the level of funding from the time, say from 1978, you would probably never make the breakthrough. You'd probably never get fusion power online, because if you're just giving just barely a trickle of money that hardly keeps the existing programs running and gives no free energy and resources to develop new systems, you're just not going to make the breakthrough. So all those were known and defined in a very serious, very rigorous report and study by the U.S. precursor to the Department of Energy. So a U.S. government agency coordinated this whole report. So they defined full funding, fusion by 1990. Take a slower path, fusion by 2005. If we keep the 1978 level of funding, if we keep a low level of funding, we might never get fusion. And then what actually happened? The funding has been below the level of fusion never. The funding has been, since the 1970s, and especially since the 1980s, the funding for fusion power in the United States has been significantly below the level that was known, which would never allow fusion to be developed. So this, I take a little bit of time to emphasize this, because I really want to make the point here. Fusion power is not 50 years away. The time away is a function of the investment we make. And the investment required has been defined and clarified, and it's not been given. So the reason we don't have fusion power today is because of the policies and the intentions, not because it's some incredibly, it is difficult, there are challenges, there's no doubt about that, but we've never even made the effort to do what we know could be done to try and bring this online. So I think that's important just to clarify and put up front. And the assessment of various experts in the scientific community is that an initial generation, first generation of fusion power could be available within 10 to 15 years. If we just said today, cut out this other crap, quit wasting billions of dollars on windmills and biofuels and just utter insanity. We actually want to support a real fusion driver program. We have designs ready to be implemented. We have ideas ready to go. They just need to be funded and supported. And we could probably have an initial fusion power plant putting power on the grid operational within potentially 10 to 15 years. So that's, if you had a full-on, top-down Manhattan Project style program, who knows? It might even be accelerated a little bit quicker than that even. So this is what this is what's possible, and this is what we have to kind of make sure is clear up front before getting into some of the additional details of creating a fusion economy. But to really understand the significance of a fusion economy and why Mr. LaRouche made a fusion driver program the fourth and concluding point in his recovery program for the United States. To understand that, you have to really understand what the nature of the human species is. And you have to understand the difference between mankind and an animal. How is the human species fundamentally different and distinct from any animal species? And one way you could understand this, and this is the subject of Mr. LaRouche's work in defining the science of physical economics, the relationship of mankind, the relationship of any animal species to the biosphere, to the environment around it, is largely determined by its biology, by its morphology, by its biological structure. And the only times you see real changes in the relationship of a certain type of animal to the environment is when that animal goes through a process of evolution. And that evolution has physiological changes. It develops new traits that allow it to do more things, maybe move into new areas it couldn't live in before, eat different food resources it couldn't eat before, any number of examples. But for the human species, we demonstrate something absolutely distinct from that. The human species has the ability to willfully self-evolve through the process of creative thought. That the relationship of mankind to the Earth, to the environment around us, and ultimately to the solar system and beyond is not defined biologically. It's not defined by the physiology of the human body. It's defined by the scientific and technological understanding and discoveries of the human mind and the cultural level of society to disseminate, to understand, utilize, and disseminate those ideas, and to facilitate the ability of coming generations to generate new fundamental ideas. That's what mankind is. That's the secret of economics that Mr. LaRouche has based his entire life's work upon. And this has been understood by other great thinkers. If we have some time towards the end, I might get into some of the work of Vladimir Vernadsky, who Mr. LaRouche included as a major component of this 4 laws document that this whole class series is based upon. But Mr. Vladimir Vernadsky also recognized this unique nature of human beings, of the human species, and he referred to it as scientific thought as a geological force, or scientific thought as a planetary phenomenon. That with mankind, you have for the first time the expression of ideas, of scientific discoveries, and these are now expressed as a geological force, as a force that can shape the entire planet, as a force that shapes the entire biosphere. And that is what mankind is. So Mr. LaRouche has identified that you can map one very useful metric of human advance from this standpoint is examining the use of fire and higher forms of fire. Literally from original basic wood-burning fire. The beginning of mankind beginning to utilize, very primitive variations of the human species beginning to utilize fire to fundamentally change his relationship to his environment around him. But you can trace the progress of human society through these higher and higher forms of fire, and especially with some rapid explosions in the more recent centuries, with the utilization of various higher forms of fire of coal, utilizing coal as a power source, utilizing natural gas and petroleum as power sources, and then the big revolution that we're still sitting on the verge of fully implementing, which is the fire of nuclear reactions, which is millions of times more powerful. And to really understand the significance of these changes, these developments, it's not just more power, but at each of these stages, you open up entire new qualities of action, entire new categories of activity. Or said another way, you create, in effect, new resource bases. With the motion to higher forms of fire or higher energy flux densities, you begin to be able to utilize elements of the biosphere, elements of the minerals and materials of the earth that were of no use to you before. So you literally, mankind, through the creative development of the mind and creative discoveries, mankind creates resources by his discoveries. Resources do not exist as a self-evident or self-defined subject. What makes a resource for mankind a resource is not simply determined by its own state, but by the scientific and the technological developments of society. So that's the context to understand the significance of the fusion economy. That's what we have to understand. That's the basis from which we have to look at this. And from that standpoint, we see that today the most advanced form of fire available to mankind is fusion. And fusion is going to be the driver program that's going to transform mankind's relationship to the planet, mankind's relationship to the solar system, and provide for the needs of coming generations of a more advanced and more developed human civilization. And that has to be through fusion power, because that is the nature of human progress. That is what makes mankind mankind. So if mankind is going to progress, it has to be on the basis of what it is that makes mankind unique and makes mankind mankind. And today, right now, that is fusion power. So now I want to show a couple more graphics here to illustrate some aspects of this. Now, here quickly, just to get an initial sense, and we'll come back to some of this. Here is a comparison of the energy densities of different forms of fuel. Different fuels for different qualities of fire. And as you can see, here we're literally measuring the energy per weight. Just how much energy is in a certain weight of the fuel. Here we're measuring it in joules per gram. You could measure it in calories per pound. It doesn't necessarily matter, but you're looking at the relative changes of the amount of energy per weight of a fuel. And as you can see, wood, coal, petroleum, even hydrogen and oxygen, which is one of the best rocket fuels that exists. All of these fuels are within an order of magnitude of the same energy density. Now, coal is a good amount more energy dense than wood. You have more energy per mass per weight in coal versus in wood, but it's not all that much more. Petroleum is a little bit more, diesel is a little bit more, hydrogen, oxygen combustion is a little bit more. But then when you get to nuclear reactions, nuclear fission and nuclear fusion, you see a dramatic leap. You see a million-fold increase of the amount of energy per mass of your fuel. And this is one aspect of the power of fusion reactions, which can give you millions of times more energy per weight of your fuel than any form of chemical reaction. And as we'll get into, it's not only more energy, it's energy of a higher quality. And we'll get into what this enables us to do back on planet Earth. So to show this next graphic, let's talk about fusion. Let's talk about what fusion is. Here we see an image of the inside of a fusion reactor. And this was made obviously from two images. One image when the fusion reactor was turned off, and a second image when the fusion reactor was turned on. And they kind of do a cutout of what it looked like when the fusion reactor was on to kind of give you a comparison of the on-off conditions. Now what we have here is what's referred to as a tokamak design, kind of a donut-shaped design, where they put a hydrogen gas inside this chamber, and they heat it up to incredible degrees, incredible temperatures, hotter than the sun, potentially in certain cases. And it becomes a state of matter that's not really a gas, it becomes a plasma. And this plasma can then be, has certain electrical and magnetic properties, and it can be controlled by a magnetic field. So you can create a very high magnetic field that keeps this plasma in place in this reactor. This is one avenue for fusion development, so-called magnetic confinement fusion. This plasma, these hydrogen atoms, to get them to fuse, to get them to combine, two atoms becoming one atom, and an immense amount of energy released in that process. So this is the kind of sketch description of one avenue towards fusion power. There's additional avenues which either by utilizing lasers to compress a small amount of fusion fuel and get it to compress kind of in a pulsed system where you're shooting lasers at pellets. There's additional variations of ways you could potentially do this. But to not get into too much details on that, what we want to look at here, so this is one basic initial design type of fusion reactor, which is utilizing magnetic fields to confine and control this plasma, heat it up, get the hydrogen nuclei to fuse, and then release immense amount of energy. But what we have to understand is that not all fusion fuels are created equal. You can put in different types of fuel into these machines, and you get different reactions. Now, if we go to the next another graphic here, here is a drawing of a few different types of fusion fuels. And we want to take a minute to examine this, because we can clearly define two eras, two types of fusion reactions. What you might call first generation or basic fusion reactions. And then beyond that, we can define what sometimes has been called advanced fusion reactions or advanced fusion fuel, or second generation fusion reactions, fusion fuel. And that's helium-3. And that's what we want to go to. We want to go towards the more advanced, the more developed form. and that has to be our driver. So now to understand that, let's just examine these different types of fusion fuel briefly. On the top, you have two types or two isotopes of hydrogen as your fuel, deuterium and tritium. Now when you fuse these, and this is the basic type of first generation basic fusion fuel that many of the fusion projects around the world have been focused upon utilizing because it's kind of the easiest to get going. Now when you fuse a deuterium and a tritium atom, you get an immense amount of energy released. But unfortunately, that energy released is in the form of a helium nucleus. So again, this is our fusion process. We're fusing two hydrogen atoms together, creating a helium atom, creating a new element, a different element in the periodic table. We're transmuting elements here, which is itself remarkable. But what you also get as a result of this particular fusion reaction is you get what is called a neutron, a single particle which has no charge, meaning it is not susceptible to being controlled by magnetic fields. If we go back, here we go to our tokamak design, we're using magnetic fields to control and confine the plasma in this fusion reactor. As soon as the fusion occurs, you have the production of a neutron. This neutron doesn't care about these magnetic fields. They don't affect it. They don't control it. Most of the energy of this fusion reaction goes into this little neutron. And this neutron then leaves the plasma. So most of the energy of the fusion reaction leaves. It's gone. It leaves the plasma itself. And because it cannot be contained by this magnetic field. And so to get the energy out of a fusion reaction with deuterium-tritium, where you get most of the energy coming out of these neutrons, you have to utilize these neutrons to heat water, utilize the kinetic energy, the heat energy of these neutrons to boil water, have that water reach a point where it becomes steam, and then use that steam to then spin a turbine to generate electricity. Now this is the same method of electricity generation that's used in coal power plants, that's used in nuclear fission power plants. This is the 20th century electricity generation technology. It is actually very inefficient. If we skip ahead to a few graphics, here is a map of the U.S. electricity generation. And you can see the sources of electricity coming in on the left there. And the width of this diagram at any point corresponds to the amount of energy involved in these processes. So you can see that most of our, the largest source of electricity generation, of energy for electricity today, is from coal in the U.S. economy today. This is the total U.S. economy we're looking at. Then you have a lot from natural gas, you have a lot from nuclear power, and you have a lot from, a good chunk from renewable energy. But most of this renewable energy is actually in the form of hydroelectric power. If you were to look at solar panels, it would be a very small sliver. You might not even be able to see it on this graph. So they call it renewable energy, but most of that, the largest source of that, is from hydroelectric power. So don't be tricked thinking that that's actually solar panels. Solar panels are incredibly inefficient, totally wasteful. Windmills are a total drain on the economy. The only reason these things exist is because they have massive government subsidies to prop them up, and they're actually a net drain on the economy. But what I want to focus on here, these are all of our fuel import, these are all of our energy sources to generate electricity in the United States. the vast majority of the energy created from these fuels is lost and does nothing. This, if you move from the left to the right, this huge chunk on the top, this large band splitting off and moving upward towards the right on the top, is the conversion losses. This is the energy that's lost in the process of the fuel reaction, boiling water to create steam, pumping that steam through to spin a turbine, and that turbine generating electricity. That process has a limit on how efficient it can possibly be. And with standard systems, maybe around 40% efficient. So maybe you get 40% of the energy from your fuel actually becomes electricity. 60% is gone. No use of it whatsoever. For this graphic here, for the U.S. economy as a whole, only 37% of our energy created from our fuels becomes electricity, and the other 63% is not used at all. It's lost as waste heat in the conversion loss. So I go through this just to make the point that what we're talking about with these first generation fusion fuels is still within this domain. It's still within this generating heat, using heat to boil water to create steam, using steam to turn a turbine to generate electricity. That's the we might call a 20th century method, and utilizing fusion reactions which generate a lot of neutrons. Now, neutrons can be useful for a lot of things. We can discuss that in more detail in the Q&A or other discussions. But to power the global economy, we're going to need a lot of electricity. And if we're trying to generate that electricity with fusion reactions where most of the energy is in neutrons, we're effectively trying to do fusion within a 20th century mode, a 20th century mode of operations, which ends up being very inefficient and really does not rise to the potentials of thermonuclear fusion reactions. So therefore, we come to second generation fuels, advanced fusion fuels, namely helium-3, which is the best fusion fuel available to mankind right now. I'm going to pull this illustration back up again so people can compare 4 different types of fusion fuel reactions. Up top, again, this deuterium-tritium, most of the energy comes from the neutron. If you fuse deuterium and deuterium, you still get a lot of neutrons, and overall you get less energy. But if you go below to the second 2 reactions, either helium-3 and helium-3, or deuterium and helium-3, all of your products from your fusion reactions, everything that's generated from the fusion reaction remains a charged particle. It remains something that's subject to magnetic fields, meaning it can be kept within our plasma, kept within our fusion plasma. Most of the energy isn't just lost out of the magnetic field of the plasma structure itself. So we're keeping the energy within the plasma of the fusion reaction. Hopefully this is not getting too detailed and technical, but I do want to make sure we're clear on the difference between these first generation and second generation fusion reactions to really understand and scientifically understand the significance of helium-3 and why Mr. LaRouche says helium-3 is what we need to go for immediately. That's what needs to define our whole program, because this is a fuel that will give us the highest energy flux density possible for an advanced fusion economy. Now, because all of the energy is maintained in this fusion plasma, we have other methods of generating electricity. These are generally referred to as direct conversion. So conversion being, how do you convert the energy from your fuel reacting into electricity? The steam cycle is an indirect conversion. You're generating heat to boil gas, to spin a turbine, to generate electricity. With advanced fusion reactions, you can use the properties of the plasma itself to generate electricity. So you can immediately go to higher levels of conversion efficiency. You can immediately have a much higher percentage of your energy being converted into electricity. The current steam cycle systems may be around 40% efficient. With this type of advanced helium-3 fusion fuel, we could be more like 60, 70, or 80% efficient. So this is not an insignificant boost just right there in the conversion efficiency, but it also signifies, again, what I would call a 21st century method of fusion. We're actually moving beyond the turbine cycle, which has been in use for the past century for electricity generation. And we're beginning to move into a domain where we're working with the properties of the plasma itself and entering a whole domain where we're utilizing controlled high-temperature plasmas more directly. Now that will end up having broader benefits beyond just electricity generation, but just for this initial point of illustration, the electricity generation is not insignificant. We get a greater boost if we go to advanced fuels, which enable us to utilize these properties of the plasma directly for a 21st century fusion economy. So that's, and then we'll also get into the benefits for space travel and other things. So, but the point is, that's the basis for helium-3 being the most, it's of a class of fuels that is this advanced fuel, but it's also the one with the lowest ignition temperature. It's the easiest to get it to fuse relative to some more other exotic options. So for mankind today, what Mr. LaRouche has said, which is absolutely correct, is that the best, what has to define the development of the global economy is a helium-3 fusion driver program. That is the most accessible, advanced fusion form that we have available to us. Now the only challenge comes, the main challenge comes, helium-3 is very sparse on Earth. There's not a lot of helium-3 around on the planet Earth. We actually get a little bit from the decay of radioactive elements in nuclear weapons, and we actually have enough to kind of play with a little bit to do some testing and various things. But for the most part, there isn't a whole lot of it on Earth. But it is produced by the sun. The sun actually generates helium-3 in its own fusion reactions, and then is spitting this helium-3 out into the solar system, and has been doing so for billions of years. Now the Earth has a magnetic field, so this doesn't really reach the Earth's surface. The Earth's magnetic field keeps it away. But the moon does not have a magnetic field. And the moon, therefore, has an immense amount of helium-3 embedded in the lunar soil, trapped in the lunar regolith. And it has been estimated that the amount of helium-3 on the moon could power the entire Earth for 10,000 years. I mean, quite honestly, that's almost a meaningless number, 10,000 years. We have no, assuming a natural, healthy growth process for human society, we have no idea where mankind's going to be in 10,000 years. You look back 10,000 years, where were we then? Look back 300 years, 500 years, 300 years, where was mankind? What's been the rate of development? So we're talking about a power source that could power mankind, power the planet under current conditions for 10,000 years. Now we would probably use that at a higher rate, but that's more than enough to power an entire revolution well into the foreseeable future. And as I'll pull up a quick illustration here to show how one graphic illustration of how we might mine the stuff from the moon. This is kind of a basic schematic. There's other, this has been investigated by different scientists over the years. And basically all you have to do is scoop up the lunar dust, the lunar soil, especially the finer lunar soil, and then heat it up so it releases its gases. And then we can separate out and trap helium-3. And so this process of the development of the moon, the mining of helium-3 from the moon, the potential use of helium-3 fusion in space, which I can get to in a minute, but then also the bringing back of helium-3 to Earth to power the planet. This is what the world needs right now. This advanced fusion fuel is relatively easily accessible on the lunar surface, and what we have to do is develop the Earth-Moon space program and space infrastructure needed to develop this system. And again, this is not stuff that's science fiction. This is things we could have done decades ago. The technologies needed to develop a Earth-Moon economic interaction and the continuous exchange of material from the Earth to the Moon is not it's expensive, there's challenges, but it's not beyond the capabilities of science and technology today. It's well within the current capabilities. Now I want to illustrate with a kind of fun pedagogical example what we're talking about with the power of helium-3. And throwing around numbers becomes people's eyes just blank over it. It's hard to internalize the difference, a million-fold increase in energy density. What does that actually mean? From 1 pound of coal to 1 pound of helium-3, you get 1,000,000 times energy, 1,000,000 times the energy. Well, what does that really mean? 1,000,000 times is just a huge number. So we were looking at different examples to illustrate it, and one thing we kind of crunched the numbers for, and I think is a useful conceptual illustration of the whole thing, is looking at the water crisis in the United States from the moon and from a helium-3 lunar program. Now, very recently there's been a report done with recent NASA studies on the water loss in the Colorado River Basin. So the entire river basin area which feeds into the Colorado River, which is a massive part of the United States. It supports millions of people. It's a huge area and economic area of the United States. And they've now found that it's losing water at a rate higher than they'd expected. And much of this water loss is coming from pumping of groundwater. The Colorado River has actually reduced its flow rate over the past 10 or 15 years compared to the prior century. And as we're seeing now, we have an increased drought situation, which is becoming catastrophic. So what's been happening is there's been an increased pumping of groundwater from the Colorado River Basin, which is rapidly depleting the water supply of the entire basin. The figures, just to throw them out there, is about 7 cubic kilometers of water each year are lost from the Colorado River Basin. A cubic kilometer is, again, a very large amount, but it's something hard to conceptualize. This rate, about 7 cubic kilometers per year, is about equal to half the flow of the Colorado River. So put another way, the water needs of the Colorado River Basin could be met if the Colorado River increased its flow by 50%. Another way to conceptualize it. So this is a very significant rate of drawdown relative to the water availability in the region. But we have other methods of producing water. We can produce water with desalination. We can use energy, electricity, to remove salt from ocean water, and we can produce fresh water. We can produce the fresh water we need to support our population. Now again, the ability to do this is again defined by the energy flux density level of your economy and the global economy. This gets to some of what I was referring to earlier with changes in resource bases. At a oil or natural gas or coal-based economy, you just can't really desalinate on a large scale. You can do it in a few places, a few places that, like Saudi Arabia, will do this with oil. You can do it in a limited degree, but as a large-scale program, it just doesn't make sense in this lower energy flux density level of an economy. But once you go to nuclear reactions, and especially fusion, and especially an advanced fusion economy powered by Helium-3, you can now look at doing this on a much larger scale. So we calculated how much Helium-3 it would take to power the desalination needed to match the water loss in the Colorado River Basin. So how much Helium-3 fuel would you need to match, to desalinate the water needed to support the economic activity in the Colorado River Basin? And when you crunch the numbers, you find that it only requires 1/3 of 1 ton per year. 1/3 of 1 ton per year of Helium-3 from the moon could support the water needs, could augment the water needs of an entire river basin in the desert of the United States. 1/3 of 1 ton can be carried in the back of a standard pickup truck. So 1 pickup truck load of Helium-3, which we can get from the moon, can support the water needs and could conceptually address the water needs of an entire river basin covering many states of the United States. Now, for a comparison, if you were to try and do that with coal, you would need 6.7 million tons of coal. So 1/3 of 1 ton with Helium-3, 6.7 million tons with coal. That much coal would fill 67,000 rail cars. And I've illustrated what this would look like on another graphic here. 67,000 rail cars filled with coal would stretch the entire length of California on Interstate 5 from San Diego to the California-Oregon border. So when we're talking about millions of times more energy dense, this is what we're talking about. It would take a train the length of California filled with coal, 67,000 cars, to provide the same energy as 1 pickup truck filled with Helium-3. 1 pickup truck can match the needs, again, of an entire river basin covering many states. So that gives you one kind of limited example, but this is, you can begin to see very clearly, with an advanced fusion economy, mankind can begin to take over the water needs of the planet. We can manufacture and provide our own water requirements through the use of fusion power. And instead of being dependent upon the variations in precipitation and the existing deserts and the existing droughts, which have wreaked havoc on civilization for years. So a Helium-3 advanced fusion economy can completely transform our control over and interaction with the global water cycle. That's just one example. Just to mention briefly, these advanced fusion reactions can enable access to completely new resource bases. Whole types of metals and different vital resources which are currently not accessible to us at all, under a fusion economy can immediately become accessible to us. There's been studies of dirt, of soils in Washington and Oregon, which are very rich in iron, they're very rich in aluminum, they have titanium, they have a lot of key metals that we use all the time. But under current methods of production, they're just worthless to us. We can't use them at all. They're just dirt on the ground. It means nothing to us. But with an advanced forms of plasma processing, of controlled high-temperature plasmas, similar to what you're dealing with in a fusion reaction, so kind of a fusion-era technology, you can begin to separate out the minerals you need, the metals you need, the resources you need from these soils. And so what was dirt now becomes the soil needed to support, the resources needed to support your economy. And there's a lot of examples like this. We could spend a lot of time going through this. But the point is, water, metals, resources, these things are not self-defined. They're defined by mankind's science and technology, and that can be measured very clearly by energy flux density. So a fusion economy, we can transform and overcome the resource limitations and resource needs of the planet. And that has been understood for a long time. And I want to look at a couple other illustrations of this, which go in line with some of what Jason was discussing last week. And look at the examination of what this does to your productive powers of labor. What does a fusion economy mean, and what does energy flux density mean to the productivity of your labor force? And these are two tables illustrating the historical changes in the production of iron. Now, iron has been one of the most important resources in the development of modern society. Iron as the basis for steel, steel as the backbone of any modern economy. So steel production is one of the most important components to any economy. And the main element of that is iron. Now, on the table on the left, what you see is the changes in how productive energy is. How productive is energy? Now, a standard reductionist view would just be that energy is energy. Energy defines itself. Energy defines how much work you can do. But that's not true. Energy has different qualities. And energy of higher qualities, namely higher energy flux density, can produce more, can be more productive. And this is seen very clearly on the left across the history of iron production in the United States, where the more advanced blast furnaces for iron production, which operate at successively higher and higher levels of energy flux density, higher temperatures, higher concentrations of energy use, produce more iron for the same amount of energy. Here we're measuring billions of BTUs. You could measure joules. It doesn't matter. The point is the relative comparison. The amount of work accomplished by an amount of energy is not determined by that amount of energy. It's determined by the quality of that energy. And that quality of that energy can be very often, for the most part, measured by the energy flux density. And you see a comparable expression in Table 2, where you see a similar change in the amount of iron produced per worker, per operative. And you can see a growth from 10 tons produced per worker up to nearly 200 tons at the height of the U.S. physical economy produced per worker. So again, labor is not self-defined. the productive powers of labor, the ability of one worker to produce the goods needed for society, is not just defined by the physical labor of that person, but it's the mediation of that labor through higher technologies. What Mr. LaRouche has defined as defining the productive powers of your labor force. And again, as we see in this case study illustration with iron, higher energy flux density enables a greater productivity per worker. So that's some of what we're talking about, which would also be created with a fusion economy and an advanced fusion economy. You'd have the ability to access new resource bases. You'd have higher levels of productivity per operative, per worker. You increase the productive powers of your society. So these are just a couple examples, and I want to close off on one last example here, which is looking at the applications to space itself. And again, we return to the significance of helium-3 very specifically. Because again, as I took some time to kind of labor through at the beginning, the reaction of helium-3 fuel produces charged, all the products for the most part are charged particles, so they can be controlled by a magnetic field. They can be subject to the influence of a magnetic field. Mankind can use magnetism to control what this plasma does. And the energy is maintained in that process. Now, that can become the basis for serious exploration and development of the solar system, because that can enable fusion propulsion to power spacecraft powered by fusion reactions, and then utilizing the ability of magnetic fields to push against the plasma being created by the fusion reactions to provide thrust. And you can, again, this is much more difficult with first-generation fusion fuels. Again, because you have this neutron. Most of the energy is in this neutron. It's not subject to the magnetic field, and it cannot be converted into thrust very easily. With advanced fusion fuels, helium-3, for example, as our goal here, you open up completely new types of space travel. So what does that actually mean? What does that mean? Let's look at one case study here. This is useful because this just occurred. The European Space Agency just successfully rendezvoused their Rosetta spacecraft with a comet. Now, this is the first time in the history of humanity that we've sent an object into space that has come into orbit around a comet. We've done this with asteroids, but asteroids are very different than comets. There's a lot of interesting science to be learned there about comets, what they are, how they work, what they tell us about the solar system. So it's a very important achievement. We've flown by comets before. We've kind of taken a quick flyby, snapped some pictures, and then kept going. But this is the first time an object has come into orbit around a comet, which is in the process of happening right now, this month. It started. And in a few months, their plan is to descend a lander onto this comet, which will also be a first, and will unveil certainly some new, very exciting scientific discoveries for us. So this was a very good, very important mission that has just occurred. You can probably see it all over the news. But let's take a look at what it took to do that. So here we have an illustration of the orbit of the Earth, the orbit of Mars, and the orbit of this comet named 67P. So now to get from the Earth to this comet using standard currently existing methods of propulsion, of getting around in space, took a total of 10 years. This mission was launched in 2004. And because the energy density of chemical reactions is so low, you cannot continuously propel yourself with chemical reactions. You can't carry enough fuel to do that. So what had to happen was the spacecraft had to make, as we see in this next graphic, all the yellow orbits there is the path that the spacecraft took. And the spacecraft had to leave Earth, travel around the sun, then pass by Earth again to get a kind of boost from the Earth's gravity. And then 2 years later, do a similar thing by Mars, pass by Mars and get a boost from Mars's gravity. And then 2 years after that, get another boost from the Earth's gravity by intersecting the Earth in its orbit again. And then 5 years after that, finally arrived at the comet for a total of a 10-year trip. So it took 10 years to get from the Earth to this comet with standard propulsion systems. Now again, this is not to belittle the significance of this particular mission, because the science is going to be very interesting. But it illustrates how absurd chemical propulsion is for getting around the solar system. If this had been a comet that was on an impact trajectory with the Earth and threatening human civilization, and we only found out about it with not that long of a warning time, we would rather not wait 10 years to be able to get there. Asteroid and comet strikes occur. They hit the Earth. They'll hit the Earth again. They've caused mass extinctions before. And mankind is going to have to be able to deal with these problems as part of mankind's mission on the planet and in the solar system. And chemical propulsion simply will not suffice for that objective. If mankind is going to develop the solar system, as mankind must do to ensure the defense and the progress of human civilization and the development of the planet Earth, then mankind has to go to fusion propulsion. Now, a helium-3 fusion propulsion system could potentially get from the Earth to a comet like that potentially on the order of a week, 7 days. Could be quicker under certain circumstances, could certainly be a little bit longer, a couple weeks, a month, a couple months. But you're talking about 1 or 2 months down to a couple weeks compared to 10 years. It's just a ridiculous situation we're in now with respect to our ability to access and develop the solar system. So that's just another illustration. If we're going to move out into the regions surrounding our planet and begin to explore and develop and utilize this whole territory of the inner solar system, which is what mankind is going to have to do to progress, we're going to need, again, fusion power. So again, we come to the moon, and the moon as the power station for the future of mankind. Helium-3 on the moon is the most advanced, highest energy flux density fuel source for fusion power that mankind immediately has accessible to him. It will require work to develop. It will require significant investment, and it will happen the most quickly with international cooperation to collaborate in achieving these common objectives. But this is what will define the capability of mankind to address his needs on Earth and in the solar system. Now, I wanted to end by referring back to some of what Mr. LaRouche focused upon in his 4 Laws document. And in particular, he made a rather interesting emphasis on the work, again, of Vladimir Vernadsky, who was a Russian scientist who is somewhat of a contemporary of Einstein, around Einstein's generation. A little bit older, I believe, if I'm correct on that. And he's a pivotal individual in the development of modern science. And Mr. LaRouche points explicitly to Vernadsky's view in his 4-point policy memorandum, which is the basis of this entire class series. And from this perspective, Mr. LaRouche says that man is mankind's only true measure of the history of our solar system. That is the same thing as the most honored meaning and endless achievement of the human species, now within nearby solar space, heading up to the mastery over the sun and its solar system, the one discovered uniquely as a matter of fact by Johannes Kepler. A fusion economy is the presently urgent next step and standard for mankind's gain of power within the solar system and later beyond. So I think if Vernadsky were alive today, he would be viewing this perspective with the most profound significance. That what Mr. LaRouche says here as mankind heading towards a mastery over the sun and a mastery over the solar system is not just some wild, harebrained idea, but that is what's happening. That is what mankind expresses, and that is the future of mankind. And Vernadsky would have seen this, I fully believe, in very clear and uncertain terms. Vernadsky defined the domain of activity of mankind as what he called the noosphere. He had earlier defined the domain of activity of the animal domain as the biosphere. And he defined very clearly that mankind expresses a higher power than the biosphere. That the noosphere, the domain of mankind's effects, the domain of mankind's activity, subsumes and controls the development of the biosphere. And as we were saying at the beginning, this is enabled by the power of human scientific thought, of cultural thought, something absent in the animal domain, and something that uniquely creates the power, this willful, creative capability of mankind, enables mankind and defines the destiny of mankind as being a controlling force and a responsible force for the biosphere and the planet as a whole. And Vernadsky, in no uncertain terms, very clearly defined this in many illustrations, showing the power of mankind to reshape the planet. That the activity of human thought, as he said, was a geological force that is more powerful than the biosphere alone. And you see this in the development of regions of the planet. You see this in the fact that mankind can create lush gardens from deserts. You see this in the fact that mankind can create agricultural production way beyond what the biosphere could do alone. You see this in the fact that mankind can control resources and create more highly organized structures of metals and other resources than would ever exist otherwise, and utilize these for the benefit and the development of both mankind and the biosphere. So Vernadsky very clearly defined what was then an undeniable process of the power of mankind overtaking the planet. But until this point, that entire process has been defined by mankind's relationship with the planet, with the biosphere. With a fusion economy, we're literally beginning to see the prospect of mankind not just overtaking and becoming more powerful than the activity of the biosphere, but of the solar system and the sun as a single process, as Mr. LaRouche defined, as Kepler discovered it as a single process. So you're looking at the sun and the solar system as a single unified process, largely powered by the activity of the sun itself. With fusion, and with the prospect of a lunar helium-3 fusion economy, mankind is beginning to take actions that supersede the influence of the sun on the planet Earth and beyond. You see this, for example, in fusion reactions themselves. The temperatures we've been able to achieve, albeit briefly, but future developments can ensure it can be sustained for longer periods. We've been able to achieve temperatures significantly hotter than anything we know about the sun. We've been able to achieve densities of matter in laser fusion experiments greater than the densities at the core of the sun. We've been able to achieve brightnesses brighter than the sun. We've been able to achieve controlled levels of energy flux density higher than the sun itself. The power of human noetic fusion, magnetic confinement fusion, per size, per mass, per scale, is more powerful than the gravitational confinement fusion of the sun. The sun's obviously much bigger, so in total terms, it's much higher. But the literal energy flux density, the energy per mass per time, relative to the size of the reactions, for mankind is much higher. The magnetic confinement of mankind can greatly surpass the energy flux density of the gravitational confinement fusion of the sun itself. So we're beginning to enter a domain beyond the capabilities of the sun. And we can use that power on Earth for, as I was describing here, desalination. But then what is desalination? Until this time, the entire global water cycle has been powered by the sun, by solar activity. All of your lakes, all of your rivers, all of your glaciers, all of your groundwater, all of your rain and snow, all the water you know of on any land mass on the planet was put there by the activity of the sun, by solar evaporation, solar desalination of ocean water, and precipitation powered by solar activity. It's been a totally solar-powered hydrological cycle. With fusion power, mankind can be the first force ever on the planet to manufacture its own fresh water and to create entire new water cycles, bringing fresh water into the land, onto the land masses, and empowering entire new developments of life and of human life through the creation of his own water cycles. This is literally mankind beginning to overtake the otherwise domain of influence of the sun on the planet Earth. These types of fusion propulsion systems, possible with fusion-powered spacecraft, is something beyond any capability of orbital travel otherwise. That the sun's gravity determines the orbits of the planets, determines the motion of planetary bodies, asteroids, comets in the solar system. These are all defined by simple orbital systems. The Rosetta spacecraft I just illustrated was a simple, relatively simple orbital system with a few boosts along the way. Fusion propulsion enables an entire new class of activity, completely absent from the solar system outside of mankind's ability to create it. The ability for continuous acceleration, to constantly accelerate to greater and greater speeds, to travel through interplanetary space in a way otherwise impossible. And a lot more can be said on the details of this and other expressions. But the point is, you see multiple expressions of the potential of mankind under a fusion economy to begin to take on and overtake types of activity and actions which were prior solely to the domain of the sun and the solar system itself. And so I would think, based upon my understanding of Vernadsky's work and Vernadsky's thought, that what we're talking about here, what Mr. LaRouche is defining here, can also be discussed as the emergence of a completely new stage of the noosphere, a completely new stage moving beyond what we might call the terrestrial noosphere, the interaction of mankind with the planetary system more directly, and the beginning of an age, what we might call the noosphere of the solar system, and mankind beginning to actually be a force on the scale of and surpassing the activity of the sun itself. And so that's what we're talking about with these 4 laws. And that's what we're talking about with a helium-3 advanced fusion economy. It will take, as Mr. LaRouche said, work and time to get there. But we must define this as the goal, as the mission, which then defines and subsumes and determines all the steps between now and there to achieve that goal. Because this is what will enable us to do this. This is what will enable the next qualitative stage of human society. And that is economic value. That is progress. That is what determines the needs, the ability to meet the needs of society. So we have to set, Mr. LaRouche has been very clear, we have to set that as the mission, and we have to fully support any nation with the morality and the forward thinking to set that as a goal, which namely so far has been China. And China's activity is a is a high mark for the global economy currently in orienting that direction. So our fight here is to join that mission, to get this other crap out of the way, get this piece of crap Obama out of the way, break from this insane collapsing system, and embark in this direction. And Mr. LaRouche has given us the policy pathway to do that in his 4 laws. So I will end it there, and I'll be happy to take any questions or discussion based upon that.